Having proven the sine and cosine addition formulas, we're now going to prove the tangent addition and subtraction identity, and then we're going to show you how it can be applied. Let's start with the tangent addition and subtraction identities. We're going to start this proof by using your knowledge that the tangent is equal to the ratio of the sine to the cosine. So we're going to rewrite tangent alpha plus beta as sine alpha plus beta divided by cosine alpha plus beta. Since we already have proven the identities for sine of alpha plus beta and cosine of alpha plus beta, the sine and cosine sum identities, we're going to substitute those in. For sine alpha plus beta, we're going to put sine alpha cosine beta plus sine beta cosine alpha. And then for cosine alpha plus beta, we're going to put cosine alpha cosine beta minus sine alpha sine beta. So by substituting those angle sum identities, we can rewrite it. Now we need to find something that's going to kind of cancel out things and simplify it in terms of tangent. And so we're going to have to divide the numerator and denominator by something that's going to do that. And that something is cosine alpha times cosine beta, because what that'll do is that'll put a tangent in here and a tangent in there, and it'll do similar things in the denominator. So by dividing by cosine alpha cosine beta, both in the numerator and the denominator, so we do not change it, we wind up with this very complex looking thing. But it's only complex for a short period of time, because we can rewrite this sine alpha cosine beta over cosine alpha cosine beta. The sine alpha over cosine alpha is right here, and then the cosine betas actually cancel out. Over here, similarly, we have sine beta cosine alpha over cosine alpha cosine beta. The cosine alpha terms cancel out in the second part, and all we're left with is sine beta over cosine beta. A somewhat similar thing happens in the denominator. In fact, in the first part of the denominator, you can see cosine alpha cosine beta over cosine alpha cosine beta. That's equal to 1. So all of that turns into just 1. Then the second part of the denominator actually turns into two separate tangent ratios. The tangent of alpha, sine alpha over cosine alpha, and the tangent of beta, multiplied by each other. Finally, we rewrite the ratios. Everywhere we see a sine alpha over cosine alpha, we put in tangent alpha. Everywhere we see a sine beta over cosine beta, we put tangent beta. And in the end, we have tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta, which is the tangent sum formula. We use a similar process for finding the tangent of alpha minus beta, rewriting it as the sine of alpha minus beta over the cosine of alpha minus beta. So now we're doing the difference formula for tangent. And really, through this process, all the signs, SIGN signs, the pluses and minuses, change. And that's the only difference. Because as you recall, the sine of alpha minus beta is equal to sine alpha cosine beta minus sine beta cosine alpha. Similar kind of thing on the cosine. And as we work through this process for the tangent of alpha minus beta, it's the same as the tangent of alpha plus beta, only the positive negative becomes a negative over positive. So in the end, the tangent of alpha plus beta is equal to the tangent alpha plus tangent beta over 1 minus the tangent of alpha times the tangent of beta. And the tangent of alpha minus beta is equal to the tangent of alpha minus the tangent of beta over 1 plus the tangent of alpha times the tangent of beta. So we've proven the tangent angle sum and difference identities. So now that we have all these sine, cosine, and tangent sum and difference identities, let's figure out a way to use them. For your reference, here are the sine, cosine, and tangent angle sum and difference identities condensed down. I say condensed because we have a plus or minus symbol here, meaning that the sine of alpha plus beta, we're going to take the top part, sine of alpha cosine beta plus sine beta cosine alpha. For the sine of alpha minus beta, we're going to take the bottom part and use the minus sign over here. That becomes important when you're talking about cosine, because notice the cosine of alpha plus beta, if you recall, is the cosine alpha cosine beta minus sine alpha sine beta. Same thing for the tangent. Just watch those signs. So here are some uses of those sum and difference identities. And we're going to look at an example of each. So first of all, they can be used to prove other identities, notably the what's called the double angle identity, which means, for example, the sine of 2 alpha or the cosine or tangent of 2 times alpha. Also, they can be used to find exact values for angles beyond the special angles of pi over 6, pi over 4, pi over 3, and of course our quadrantal angles. So let's use this idea to find the exact values for angles beyond our normal special angles. So for example, what is the sine of pi over 12, or 15 degrees? Well, we can rewrite the sine of pi over 12, or 15 degrees, as the difference between the sine of pi over 3, 60 degrees, and the sine of pi over 4, 45 degrees, because 15 degrees is equal to 60 minus 45. Notice this, on the right-hand side, is the sine difference formula where pi over 3 is alpha and pi over 4 is beta. Substituting that in to that difference formula for sine, with those substitutions for alpha and beta, we get that the sine of pi over 3 times the cosine of pi over 4 minus the sine of pi over 4 times the cosine of pi over 3. Sine alpha cosine beta minus sine beta cosine alpha. Well, because those are all special angles, we know those values. Sine of pi over 3, square root of 3 over 2. Cosine of pi over 4 is the square root of 2 over 2. Sine of pi over 4 is the square root of 2 over 2. And the cosine of pi over 3 is 1/2. And from there, it's just a little bit of algebra to simplify that as much as we can. It's the square root of 6 minus the square root of 2 over 4. It's the exact value for the sine of pi over 12, or 15 degrees. We can also use these identities to prove other identities, notably the double angle identity, which helps us answer questions like, what is the cosine of 2 times alpha? A double angle. Since 2 alpha is equal to alpha plus alpha, we can rewrite that as the cosine of 2 alpha is equal to the cosine of alpha plus alpha. That is a cosine sum identity where we have alpha as alpha and the other alpha, the second alpha, as beta. If we substitute those values into the cosine sum identity, this is what we get. The cosine of alpha times the cosine of alpha minus the sine of alpha times the sine of the alpha. And because the cosine of alpha times the cosine of alpha is equal to the cosine of alpha all squared, and the same thing for the sine, we get what is called the double angle identity for the cosine of 2 alpha. It's equal to the cosine squared of alpha minus the sine squared of alpha. So we finished up all the addition and subtraction identities for sine, cosine, and tangent, and then showed some applications of them.